Hello, welcome to lesson 4445, polynomial functions and their graphs. The note sheets for this are provided for you in Canvas, the blank copy, so feel free to print this off and fill it in as you go. And next time we're together in class, I will also have those copies for you if you need one. All right, so we're talking about polynomial functions. Remember what a polynomial is. It's made up of a bunch of monomials. And we're going to look at specific ones today. One's in one variable. They have coefficients. They have exponents that are non-negative integers. So no fractions, no decimals, so no radicals with the variable. And the variable is not in the denominator. Also known as we said one variable. So if there's a second variable in there, we're not actually going to deal with it specifically right now. And we're talking functions, so then we're going to use function notation, that f of x rather than y, although remember f of x is equivalent to y as we look at their graphs. We're going to talk about the degree of a polynomial in one variable. And that is, when you have one variable, it's the greatest exponent of its variable. We've talked about that briefly before, or we've talked about the degree of a polynomial where you add all the exponents of the variables. Well, now if we're focusing on one variable, we're looking for its highest powered variable. And then the leading coefficient is the coefficient of the term with the highest degree, which makes sense. And that leading coefficient can be positive or negative, fraction or not fraction. And all those things will affect what the graph does. Some of that we've looked at before when we've talked about quadratics. Now, in this chart, there are different kinds of polynomials. And I'll give you a sample expression. We'll talk about what its degree is, its leading coefficient, and a sample of the graph. The graph I have drawn is not necessarily representative exactly of what this particular graph would look like. But rather an idea of, say, what a constant, a linear, a quadratic, etc. could look like. And yesterday, when you looked at power functions, you saw the basic shape of many polynomial functions. You saw that all of the even-powered functions, x squared, x to the fourth, and so on, they always had, their end behavior was always the same. Either both were positive or both were negative. Now, as we add more stuff onto the polynomial, more things happen in between. And then with odd-powered functions, whether it's x to the first, x to the third, x to the fifth, and so on, you noticed that one end behavior was positive, one was negative. Now, as we do more stuff again to the polynomial, we add more things to it, it does more things. And that's what we're going to look at in this section as well, as what is that stuff that's happening? All right, so our first one is a constant, say 9, or f of x equals 9. It's a horizontal line. It has no degree because there is no variable. It's, it'd be x to the 0 power, because remember, x to the 0 power equals 1. Anything to the 0 power equals 1. So it'd just be 9 times 1. So that means our leading coefficient is 9, and it's a graph of a horizontal line here. Linear, we've looked at those. 4x plus 9. Leading degree is 1. Leading coefficient is 4. It's a line. Looks something like that. You know what lines look like. Same thing with quadratics. It's going to be a parabola. 5x squared plus 4x plus 9. Degree is 2. Leading coefficient is 5. It's going to be a parabola. It could open up or it could open down. Cubic means it goes to the third power. Negative x cubed minus 5x squared plus 4x plus 9. Third degree, leading coefficient, negative 3. Now here, what the one in turquoise, that's the general cubic function. So as x gets smaller, y gets smaller. As x gets bigger, y gets bigger. But because I had the negative leading coefficient, that's what I drew in red. So positive leading coefficient. This would be a negative leading coefficient right there, just so you know. All right, then we have what we call a quartic function. Goes to the fourth power, quart implying 4. 2/5 x to the fourth minus 3x cubed minus 5x squared plus 4x plus 9. Degree 4. Leading coefficient 2/5. And notice the end behavior heading in the same direction, but there's extra stuff happening in the middle. And really what you notice is 1, 2, 3, you notice it crosses the x-axis 4 times. That's the most it will cross the x-axis. And we'll make note of that later on as well. And quintic, quin implying 5, 8x to the fifth plus 2/5 x to the fourth minus 3x cubed minus 5x squared plus 4x plus 9. Fifth degree, leading coefficient of 8, and notice opposite direction end behavior. And notice how many times it crosses the x-axis. 1, 2, 3, 4, 5. If I had it cross more than that, all of a sudden my end behavior would be that of an even-powered function. So that's going to be important. The general shape of the graphs of a polynomial function show the maximum number of times the graph of each function may intersect the x-axis. Does it have to intersect the x-axis that many times? No, but that's the most that it will cross. Because look at here at our cubic. It could cross up to 3 times, but right here, our basic one, it only crosses once. You can have quadratics that don't ever cross the x-axis, and that's okay. But the most it will cross will be twice. That's the point here. So if you see a 5th power function, you know you're never going to have more than 5 times that's going to cross the x-axis. And that's something you're going to want to keep in mind, because that tells us how many solutions there are to the function, and that's something we're going to look at in the second half of chapter 4. So identifying 5th power, 5 solutions, 4th power, 4 solutions, 3rd power, 3 solutions. And then we'll talk about how many are real ones, which would be visibly crossing the x-axis versus imaginary ones when we get to it. But that will help us bring our total up. So that's why it's important to understand what our functions are doing and what the degrees mean and some of those features. It'll make your work easier later on. You also notice every time I wrote these, I wrote them in descending order of powers. You can write them in any order, but the best mathematical grammar, and what you see most often, is equations written in descending order of powers. Easiest to identify the degree and the leading coefficient then. Okay, so a polynomial function, couple definitions here. A continuous function that can be described by a polynomial in one variable, and a power function is the simplest type of polynomial function. Now we're going to get to the next page. There we go. And we're going to briefly look at a couple examples. State what the degree is, the leading coefficient of each polynomial in one variable. Not a polynomial. Tell me why. All right, so the first one, 100 minus 5x cubed plus 10x to the 7th. Yes, it's in one variable. All you see are x's. I flipped it around, put it in descending order. Degree of 7, leading coefficient of 10. LC, leading coefficient. Call me lazy, I just didn't want to write it all down. All right, let's move over here to the right. 4x squared minus 3xy plus 16y squared. Can't do anything with it other than say, nope, it's not in one variable. There is a y and a y squared. Okay, down here, yes, this is a polynomial. All the x's are up in the numerator, so it's fine. We just have fractional coefficients. I flipped things around and put negative x to the 6 over 25 plus x cubed over 36 plus x squared over 18 minus 1 over 72 to have it in descending order. You'll see sixth degree is the highest degree, and the leading coefficient is negative 1 over 25. So remember, as you're trying to write the fraction, if there's no number next to the variable up in the numerator, that's a 1. All right, and then this one looks like it's written in descending order. You only see one variable, but where is that one x? It's in the denominator. Can't have negative exponents on the variable. So it still doesn't, well, technically in one variable, it doesn't fit the definition of being a polynomial. All right, now one of the other things we're going to do with polynomials is find their values. And we've done a little bit of this before, but this is just to kind of review seeing things in function notation. You can do it with numbers or with expressions. So you find f of -5 if this is your function. So this, remember, is, I'm going to use it here, the original function f of -5, replace x with -5. Just plug in -5 wherever you see x and evaluate and simplify. Pay attention, there's a negative sign. The negative needs to be in the parentheses so it gets squared or cubed, and the proper things happen with the signs. Really watch your signs. I can't say that enough. So this one simplifies down to a number, -5. Now, we move down here, g of a squared minus 1. That whole expression is going to get plugged in for x every time we see it in the function, just like they show down here. So, guess what that means you're going to have to do? You're going to have to do a little bit of FOILing. A squared minus 1 squared, that's a squared minus 1 times a squared minus 1. And then, of course, distribute. So we get a to the 4th minus 2a squared plus 1 plus 3a squared minus 3 minus 4. Simplify a squared plus a to the 4th plus a squared minus 6. Now, why don't you pause the video and solve the two problems that are in the box here and then the one on the next page. Okay, welcome back. Hopefully you paused and you solved. Now, I said find f of -4 for each function. So just plug it into both of those functions. You get numerical answers. Pay attention to the negative. I purposely picked a negative again to make sure you're paying attention to your signs. So you should have gotten 7 here and -313 as you plugged in here. Now, if you didn't, take a look at what I did with solving and make sure that you appropriately squared and cubed and watched those negative signs as you worked. Now, there's also ones with variables thrown in over here on the next page. So c minus 2, I kept it a little simpler. So you have to FOIL here when you plug in. C minus 2, that whole quantity is squared. Don't distribute that squared over the addition or subtraction sign. FOIL it out, which is what I did. Then I cleaned it all up. C squared minus 4c minus 5. Now, keep in mind that you've got this piece right here. It will come in handy. Or that it's c squared minus 4c plus 4. That will come in handy for you over here in this other problem, right? You should have ended up with a final answer of c cubed minus 4c squared plus, oh wait, no, sorry. Here's your final answer. I apologize, it's right there. That was where I had done a little work, down on the bottom. 4c cubed minus 27c squared plus 62c minus 49. Well, here you had to cube c minus 2. And here you had to square it. Well, we already squared it over here. So I just used that information to help me with my cubing. And notice I had to then come down here for the rest of my work. And then I simplified, I expanded it all out, and then I cleaned it all up. So it's more of a nuisance type of problem than anything as far as its length. It's not super hard. Just remember to multiply accurately, watch your signs, and watch your powers. All right, you're going to have a little bit of that to practice today in your assignment.